Good morning, everybody. My name is Michaël Nicolai. I'm a PhD student in University of Ghent in Belgium, and I'm going to talk about bird coloration. We have 10,000 species of birds, and the coloration patterns are almost as diverse as the numbers of species, with species having colorations that cross the entire rainbow spectrum. But today, I'm not going to talk about those. Instead, I'm going to talk about seabirds, which also have plumage that cover the whole spectrum, but in this case, the grayscale spectrum, with plumage going from black to gray and brown over to white, but not those bright colors, those beautiful colors we saw before. And if you look at the wings in particular, you see that the diversity is especially low, with many of these birds having convergently evolved dark wings. But the reason why these birds evolve dark wings isn't quite known yet. So there's two ways to look at this. The first way is looking at it from a biologist perspective, which I am one of. And we see dark wings and we immediately think, okay, dark wings heat up more than white wings. It might have something to do with thermoregulation. But we know that the pigment, which is responsible for this, so melanin, also protects against UV. And furthermore, melanin also is known to protect against feather abrasion. But if you look beyond the pigment itself and just look at the coloration, you often see that there's also counter shading involved. So one of the other explanations that have been proposed is that these dark wings are basically a form of camouflage. The engineering perspective is completely different. They have been looking at heating up wings and seeing that they increase flight efficiency. And knowing that wings heat up more, or black wings heat up more than white wings, they suggest that this might be happening in birds. But the problem is that they have been testing at high wind speeds and not on birds, which have completely different properties compared to models or airplane wings. So we set out, so we meaning me and some colleagues, to try and find out whether or not dark wings increase flight efficiency. So the group that we chose to investigate this question is the seabirds. And why did we look at seabirds? First of all, I already explained this. They convergently evolved similar wing patterns. You have black albatrosses, you have black gulls. So this often, this pattern has evolved multiple times. Furthermore, if we want to look how the sun influences heating and the possible relationship with flight efficiency, it's important that these birds fly during the day. And we know that most seabirds are actually day active. They also fly low. So every second longer they can stay in the air means a lot of them, and especially since they travel long distances. So every bit of increase in flight efficiency has strong influences on the overall energy uptake or energy necessities that this bird might have. So before we go into the results, I think it might be useful to explain flight a bit, or the theoretical background. So flight is a balance between forces. The first one being weight. This is the force that keeps you on the ground. Then you have lift, which is the force that counteracts weight. You have drag, which prevents an object going forward, and you have thrust to overcome this drag. So basically, in order to fly, you need lift that is higher than the weight, and you need drag that is lower than the thrust. And the ratio of these two, so the lift to drag ratio, is a measurement of flight efficiency. It's also known as the glide ratio, because in gliding, it equals to the ratio of the height over the distance. So a high lift to drag ratio means that you can fly longer. And because of this, we use the lift to drag ratio as our metric of flight efficiency. So what we did next was we prepared two wings an adult gannet wing and a juvenile gannet wing and placed this in a wind tunnel. And we looked at the lift to drag ratio, so flight efficiency at different angles, different velocities, and then heated versus non-heated. And what we found was that heated wings increase flight efficiency. So we had a higher lift to drag ratio. And the interesting thing is that this was present for all angles, all wind speeds, and at the low wind speeds, this effect was sometimes even as high as between 15 and 20% for the adult gannet wing. When we look at the juvenile gannet wing, we see a similar pattern. The one exception being the zero angle, but this has something to do with how we mounted the wing. So this is not really representative. But again, we found effect for the other angles, effects for all wind speeds, and this increase in flight efficiency was this time even higher, so between 20 and 30%. So while we initially thought, okay, this proves it, darker wings have a higher flight efficiency compared to white wings. The comparison is not completely fair because the shape is different between those two wings. So this has important aerodynamical consequences. So we couldn't really compare the juvenile with the gannet wing. So to solve this, we actually tried removing the melanin from the juvenile wing and adding synthetic melanin on the adult gannet wing. And while the coloring itself worked perfectly, it really looked natural. The problem was that the shape changed in the process of removing and adding melanin. And this had consequences on the lift production, as you can see here. So basically, we couldn't compare a black wing with a white wing, but we know that darker wings heat up more than bright wings. And we know that the effect we measured is temperature dependent. So it's safe to say that darker wings have a higher flight efficiency. So this is really cool, but the problem is it doesn't mean that something is more efficient, that evolution takes advantage of this, right? So we tried to think of which birds might benefit. And to do this, we looked at wing loading, which is the mass of a bird over the surface area of its wing. And we use this metric because we know that it's related to cruising speed, so the speed at which flight is most efficient. And to explain this easily, you can basically say that high wing loadings means that you have difficulties flying at low speeds, and low wing loadings means that you fly easily at low wind speeds, but have difficulties flying at high wind speeds. This explains, for example, why albatross have difficulties taking off, but also why butterflies fly at low wind speeds, not high wind speeds. The Boeing consumes a lot of energy when taking off, but once at cruising speed, which is really high, it's quite efficient. But also why humans, which have high wing loadings, don't fly at all. So our hypothesis was that if evolution would take benefit of this effect, it would be most obvious in birds with high wing loading. So basically that high wing loading birds would be darker. So in order to look at this, we needed to quantify darkness. So we had museum specimens of 110 species, around 200 skins. And what we did was delimit distinct color patches on each of these wings. For example, in the adult gannet, this would mean we have one black patch and one white patch, but this could also be a brown patch or a gray patch. And for each of these areas, we calculated the relative area, as well as the reflectance for each of these patches. And then for each patch, we multiplied the reflectance with the relative surface, with the relative area of the patch, and then took the sum of all patches on a wing to calculate a wing darkness. And then we used phylogenetically controlled correlation analysis to see whether darkness was correlated with wing loading. And what we found was actually interesting because in the visible spectrum, we found a really strong effect, but this effect was absent when we included infrared reflectance. But when we looked at the variation in reflectance in the infrared, we found that basically a black wing looked almost identically to a gray wing, to a brown wing, to a white wing. So there was no difference at all. So if selection would happen, it would have to happen in the visible spectrum. And this is exactly what we see. Looking at this figure, though, you can also see that some low wing loading birds also evolve black wings. This is not completely unexpected, first of all, because you have phylogenetic inertia. If suddenly a black-winged bird with high wing loading becomes, gets a smaller wing loading, it doesn't necessarily mean that evolution can follow and evolves a wider wing. On the other hand, not only high wing loading birds benefit from this effect. So every bird can utilize an increase in flight efficiency. It's just that these high wing loading birds benefit most, so they have more selection acting on them. So the next question we had was, okay, so we know that birds gradually evolve darker wings, possibly related to becoming more efficient. But how did they do this? So the first option would be to increase the number of dark patches. For example, shown here in the gannet wing, first you have only one dark patch, but it could be that you increase the number of dark patches and suddenly you have a completely dark wing. But another option would be that you already have a wing that has patches with melanin in it, but the melanin content is so low that you have, for example, a grayish color. And then you gradually increase the number of, well, the melanin content, and you also get a completely dark wing. So we looked at reflectance at different patches and how this evolved. And we found that actually almost all patches already contained some melanin, but this gradually increased. So what happened in seabirds is that the ancestral bird probably already had grayish wings, or at least some melanin in all patches, and this melanin content increased gradually to get the dark wings we see now. So to conclude, we tested whether or not darker wings have an increased flight efficiency, and this because they heat up more. What we found that heated wings actually increase flight efficiency, and this for all angles, all speeds, and with an effect of all that goes higher than 20% increase in flight efficiency. We also found that evolution took advantage of this effect and evolved high wing loading birds to have darker wings, and this by increasing the melanin within the patches. And this has interesting implications for other birds that have dark wings, especially those that either fly during the day and or migrate long distances, and in particular birds that soar, such as birds of prey. And while we started this project by looking at an engineer perspective, we also think we still can add some added benefit to engineers as well, because they've been looking at high-speed aircrafts. But we also show that this effect is present at low-speed aircrafts, and that the effect is actually quite high, and giving the rising importance of, for example, electronic aircrafts and drones, which fly at low wind speeds. We think that this might have important implications as well for engineers. So coming back to my initial slide with the question of why do these birds have dark wings? I hope you now see that one of the possibilities might be that these dark wings increase flight efficiency. And with this, I would like to thank you for your attention. Should you have any questions, feel free to contact me. Thank you for your attention once again.